In this first problem with connected objects and friction, we have two boxes that are being pulled across a rough surface by a force of 50.7 newtons that's acting to the right. So the first thing to do is to calculate the weight of each one of the boxes. So the weight of the first box is 18.2 times 9.8, which is 178.36 newtons. The normal force that's acting on that box, because there are no other vertical forces acting, is also 178.36 newtons. On the 2.55 kilogram box, if you take its mass and multiply by 9.8, you get 24.99 newtons. Again, for the same reason as before, the normal force on this box balances out its weight, so that's also 24.99 newtons. The next thing to do is to look at the force of friction acting on each of the two boxes. So you're told that the coefficient of friction between each of the boxes and the ground is 0.2. Even if they weren't both the same value, it would be no different to calculate it. You would just have to be careful which box you were looking at and make sure that you use the correct coefficient of friction. So I'm going to call this box 1 and box 2 just so we could keep them apart. So we have the force of kinetic friction on box 1 pulling to the left on box 1, and we have the force of kinetic friction on box 2 pulling on box 2. And we can calculate each of those values. The force of kinetic friction on box 1 is going to be the coefficient of friction between box 1 and the ground, which is 0.2, times the normal force acting on box 1, which is 24.99 newtons, which is 4.998 newtons. The force of kinetic friction on box 2 is the coefficient of friction between box 2 and the ground, which is also 0.2. But again, if they weren't the same, you would just make sure that you use the correct value, times its normal force, which is 178.36 newtons, which is 35.672 newtons. Now, to figure out the acceleration of the boxes, one of the easiest ways of doing this is to treat the two boxes as a single object. And that single object would have a total mass of 2.55 plus 18.2, or 20.75 kilograms. And that single system is being pulled to the right by a force of 50.7 newtons. But then, because there are two friction forces that are acting to the left, we need to make sure that we include both of those forces. So we have that first friction force and the second friction force, which we found above. And so the net force acting on that entire system, again, I'm going to set this up so that the right is the positive x direction, is 50.7 newtons plus negative 4.998 newtons, which is FK1, plus negative 35.672 newtons, which was FK2. If you add all those together, you get 10.03 newtons. You also know that the net force acting on the system is the total mass of the system. Again, we need to make sure that we use the full 20.75 kilograms because that whole system is moving together as one unit, times the unknown acceleration A. And so if we combine those together, we have 10.03 newtons equals 20.75 kilograms times the acceleration, or we get that the acceleration of the boxes is 0.48337 meters per second squared. So solving this problem is no different than the problems where there is no friction. You still are able to treat it as the system and look at all of the external forces acting on the system and use all of those external forces to get the net force. The only difference is the two forces of friction that were acting in this are external forces, so you need to make sure to include them. And then just like in other connected object problems, once you have the acceleration, if you want to find one of the internal forces, so here that would be the tension in the rope connecting the two objects, you have to look at one or the other of the boxes. It doesn't matter which one. So the one that I'm going to choose to look at is the 18.2 kilogram box. On the 18.2 kilogram box, there was the 50.7 newtons acting directly on it. The force of kinetic friction between that box and the ground is acting directly on it also. This was the one that was 35.672. And we have the unknown tension that's pulling to the left. Again, I'm going to set this up so that the right is the positive x direction. So the net force acting on just that single box is positive 50.7 newtons plus negative 35.672 newtons plus negative t, and the net force acting on just that box is the mass of just that box, 18.2 kilograms, times the acceleration that we calculated before, which is 0.48337 meters per second squared. And so this net force that's acting on just this box is 8.7974 newtons. So combining those two pieces together, we have 50.7 minus 35.672 minus t equals 8.7974. Or solving that for the tension in the rope, we get 6.2306 newtons. Now, at this point, you're done. But if you wanted to double check things, you could look at the 2.55 kilogram box. On that box, you'd have the unknown tension pulling to the right, and we would have had the 4.998 newtons acting to the left. That was the first friction force. And I'm not going to go through and solve the equations completely, but the net force would have been the tension minus 4.998, which you could plug that tension in. And the net force on this would also be 2.55 times the acceleration. It's the same acceleration as before, 0.48337. And you can see that those two things are going to equal each other. Again, looking at this, I could combine these two equations together and solve for t, or I can take this t and plug it in. Either way, I see that that is going to give me a solution. That tension acting on just this box is going to cause it to have the exact same acceleration that we calculated previously. Again, in these types of problems with connected objects, just go through, make sure you look at all of the forces that are acting, but most importantly, make sure that you go through and you include these friction forces. Make sure you're looking at the correct normal forces, make sure you're looking at the correct coefficients of friction. But if you do include all of the forces that are acting, you will be able to solve the problem just like the problems where it was frictionless. In this next problem, instead of having some things that are connected together by a rope, we have something where several boxes are being pushed together, and we're going to end up looking at the contact force between the two boxes that are on the right-hand side. So we're told that we have a force of 83 newtons that's pushing on this system, and ultimately we're asked for the contact force between these two boxes on the right, the 2.4 kilogram box and the 9.4 kilogram box. Again, I'm going to label these boxes 1, 2, and 3. It's going to make it a little bit easier when I go through and try and find different forces. The first thing that I need to do is calculate the weight of each of the boxes. So the weight of the 2 kilogram box is going to be 2 times 9.8, or 19.6 newtons. The weight of the 2.4 kilogram box is 2.4 times 9.8, or 23.52 newtons. And then the weight of the third box is 9.4 times 9.8, which is 92.12 newtons. Again, this is a flat surface. We're pushing horizontally on it, so the normal force on each of those boxes due to the ground is going to just balance out the weight of each of the boxes. So the normal force due to the ground pushing up on box 1 is going to be 19.6 newtons. The normal force of the ground pushing up on box 2 is 23.52 newtons. And the normal force acting on box 3 due to the ground is 92.12 newtons. And the reason I'm making sure that it's very clear that it's the normal force due to the ground is because the contact force between boxes 1 and 2 and the contact force between boxes 2 and 3 could also be described as a normal force. It's the normal force of box 1 pushing on box 2, or 2 pushing on box 1. The normal force is anytime you have one object in contact with another surface. You can consider one of the boxes to be the surface. But here we're looking at the normal force due to the ground, and each of those normal forces balances out the weight of each one of those individual boxes. Now, on each one of these boxes, there's going to be a force of friction. So I'm labeling them FK1, FK2, and FK3 for the force of kinetic friction on box 1, box 2, or box 3. Again, in this problem, we're told that the coefficient of friction between each box and the surface is 0.094. And they're making it easy by making all of the coefficients of friction the same, where it's the same type of block in contact with the same type of ground, so it's the same roughness, same coefficient of friction. but there's no reason that it would have to be. Again, if each one of them had a different coefficient of friction, you would just make sure that when you're looking at the force of friction on box 1, you would use the coefficient of friction between box 1 and the ground. And so we need to calculate each one of those forces of friction. The force of friction on box 1 is 0.094 times 19.6, which is 1.842 newtons. The force of kinetic friction on box 2 is 0.094 times 23.52 newtons, which is 2.211. The force of kinetic friction on box 3 is 0.094 times 92.12, which is 8.659 newtons. The next step is going to be to treat this all as one system. The total mass is the 2 kilograms plus the 2.4 kilograms plus the 9.4 kilograms, which when you add those together, you get 13.8 kilograms. Again, that's the total mass of the system since it's all moving as one single object. On that system, we have this 83 Newton force pushing to the right. So on the system, just to draw the normal free body diagram where the tail of the vector is on the object, we have this 83 newtons that's acting to the right. Again, I'm going to set this up so that the right is my positive x direction. And then on the system, I have 3 forces that are acting to the left. I have each of the 3 friction forces. Again, if I'm looking at all 3 of the blocks together as one single object as my system, then the force between boxes 1 and 2, or the forces between boxes 2 and 3, those are internal forces, so I don't include those on my drawing. On this free body diagram that I'm looking at here, the only thing that I'm looking at is the external forces acting on this. So the 83 newtons is an external force pushing the system to the right. These 3 friction forces are all external forces acting on the system to the left. So then we need to look at the net force on that system. So the net force on the total system is positive 83 newtons. And then I need to add the 3 friction forces. Each one of them is going to be negative. So I have friction force 1, which is going to be negative 1.842 newtons. I have friction force 2, which is negative 2.211 newtons. And I have friction force 3, which is negative 8.659 newtons. And together, if I add all those together, I get 70.288 newtons. Again, 83 plus the 3 negative forces ends up being 70.288. And then the net force acting on the system is also the total mass of the system, 13.8 kilograms, times the unknown acceleration of the system. And if I take and I combine these 2 things together, I get 70.288 equals 13.8 times A. Or I get that the acceleration of each one of the boxes is 5.0933 meters per second squared. Now, I was not told that I needed to find that. We're just asked to find the force of the 2.4 kilogram box on the 9.4 kilogram box. But to be able to find that force, I first needed to find the acceleration of the system. And then once I get that acceleration of the system, then I need to look at either box 2 or box 3. I can't just start by looking at box 2 because box 3 pushes box 2 to the left, and I don't know that force, that's what I'm looking for. And box 1 pushes on box 3 to the right. If I go back and look up at this, I have box 3 pushing on box 2 to the left, and I have box 1 pushing on box 2 to the right, and I don't know either of those forces. The force of 1 on 2 is not just this 83 newtons. Some of this 83 newtons is being used to accelerate box 1, and then some of it is transferred over to box 2. And so whenever you're going to try and find one of these contact forces, the easiest thing to do is to start at one end or the other end. And so for this, I'm going to look at box 3. That's going to be the easiest. I can just do this in one step. If I look at box 3, I need to look at all of the individual forces that are acting on box 3. So box 3 was the 9.4 kilogram box. Again, I'm not going to worry about the force of gravity and the normal force because those two forces cancel each other out. But pushing on box 3 to the right was box 2. So I have the force of 2 on 3 pushing to the right. That's what I'm looking for. And then acting to the left on box 3 is the force of kinetic friction between box 3 and the ground, which we found above was 8.659 newtons. Again, setting this up so that the right is the positive x direction. We have that the net force on just this box is the force of 2 on 3 plus negative 8.659 newtons. We also have that the net force on just this box is the mass of just this box, 9.4 kilograms, times the acceleration of this box, which is 5.0933 meters per second squared, which if you multiply those together, you get 47.877 newtons. And so then combining those two equations together, I have 47.877 equals the force of 2 on 3 minus 8.659 newtons. So the force of 2 on 3 is 56.536 newtons. And this is ultimately what we were looking for. We were looking for the force of box 2 on box 3. Again, we could go back. We could have found the force of box 1 on box 2. We can look at any of these contact forces. Looking at this, if I look at box 1 by itself, there would be 83 newtons pushing on it to the right. There would be this friction force acting to the left. And there would be box 2 pushing on box 1 to the left. Those would be the three forces that you would look at together if you were looking at box 1. If you were to look at box 2, you would be looking at box 1 pushing on box 2 to the right, you would have box 3 pushing on box 2 to the left, and you would also have this friction force acting on it. Again, you would need to make sure that you included all of the forces that were acting. The easiest thing to forget is to include those forces of friction. But if you went through and you looked at it, you could see that, if you looked at the force of box 2 on box 1, if we would have looked at this box on the left, if you would have calculated that force and then you would have looked at box 2, you would have got the same answer for the force of 3 on 2 that we got for the force of 2 on 3. Again, that's Newton's third law. If 3 pushes on 2 with a force of 56.536 newtons, then 2 pushes back on 3 with the exact same force in the opposite direction. In this next problem, we have one box that's sitting on a table connected to another block that's hanging from a cord. The cord goes over a massless, frictionless pulley, so we're not interested in the rotation of this pulley at all at this point in the class. But unlike when we were doing this problem earlier, where there was no friction between this block and the table, we now have a force of friction that's acting. And our job is going to be to calculate the coefficient of kinetic friction between the block and the table. We're also going to try and find the tension in this cord that's connecting the two objects. To solve this, we are not told the acceleration of this system directly, but we are told that when the masses have moved a distance of 0.4 meters, their speed is 1.3 meters per second. And so this means that we're going to need to use kinematics. These blocks moved with a constant acceleration, and so we need to use kinematics to figure out what the constant acceleration of those blocks was. We have that the blocks started at a position of 0 meters. They traveled to a position of 0.4 meters. We were told that the system starts from rest, so the initial velocity of each block is 0 meters per second. The final velocity of each block, they're moving together, so they each have the same speed at all times. So the final speed of each block is 1.3 meters per second. And we're trying to find the acceleration. We're not told the time, and that time is not going to be important for finding this. So to do this, we're going to use the equation that relates velocity and position. The final velocity squared equals the initial velocity squared plus 2 times the acceleration times the displacement. So we have 1.3 squared equals 0 squared plus 2 times the unknown acceleration times 0.4 minus 0. So if we solve that for the acceleration, we get that the acceleration of each one of the blocks is 2.1125 meters per second squared. And this hanging block accelerates down with that acceleration, and this sliding block accelerates to the right with that acceleration. In these types of problems, because we have this pulley and we have these accelerations changing directions, we really want to treat this as similar to a one-dimensional problem. we're going to pick the direction of the acceleration as the positive direction for each object. That way I don't need to worry about making one acceleration negative and one acceleration positive. I can say that each one has an acceleration of 2.1125 meters per second squared, and it's either to the right or down, but both of them are going to be the positive direction for whichever object I'm looking at. Next, I can look at this hanging block. On this hanging block, there's the downward force of gravity, which is 2.3 times 9.8, which is 22.54 newtons. And there's the upward force due to the tension in the rope. On the block on the table, there's the tension in the rope pulling to the right, and there's the force of friction between the block and the table pulling to the left. I also know that this block that's on the table has a weight of 3.6 times 9.8, or 35.28 newtons. And the normal force of the table pushing up on that block is also going to be 35.28 newtons. Again, nothing else is acting in that perpendicular direction, so the normal force here balances out the weight. Because I know this acceleration, the easiest way to do this is to look at this hanging block first and go through and calculate the tension in the rope. Looking at just this hanging block, we have the tension pulling up on it, but that's going to be in my negative vertical direction because I'm saying that down is positive. And I have 22.54 newtons acting down on it, which is going to be in my positive vertical direction. So for the hanging block, again, it's 2.3 kilograms. There's 22.54 newtons acting down. There's the unknown tension acting up. And we have a downward acceleration of 2.1125 meters per second squared. And again, I'm calling down the positive direction. So looking at this hanging block, the net force on the hanging block is positive 22.54 newtons plus negative T. Again, the tension is acting upwards, so it's negative. The net force on this hanging block is also the mass of the hanging block, which is 2.3 kilograms, times 2.1125 meters per second squared. And so if we solve that for the tension, if we combine those two equations and solve them for the tension, we get that the tension in the rope is 17.68125 newtons. The next thing to do is to look at the sliding block. The sliding block has a mass of 3.6 kilograms. There's the tension T that's pulling to the right. That's 17.68125 newtons that we just found up here. We have this force of kinetic friction that's acting to the left. We have the weight of 35.28 newtons, and also the normal force of 35.28 newtons. So for this sliding block, the net force on this sliding block is going to be 17.68125 newtons plus negative force of friction. Again, F sub k is how big the force of friction is, so the fact that it was acting to the left, and I was saying that the positive x direction was to the right, that I need to include that negative sign in the net force equation. I also have that the net force of the net force acting on the sliding block is the mass of the sliding block, 3.6 kilograms, times the acceleration that we calculated. Again, that was the 2.1125 meters per second squared. And so, combining those two together, I can solve for the force of friction. So I have 17.68125 minus the force of friction equals 3.6 times 2.1125. If you solve that for the force of kinetic friction, you get a value of 10.076 newtons. Now, in this problem, we weren't asked what was the force of friction acting on the sliding block. We were asked for the coefficient of kinetic friction between the block and the table. And to do that, we use that the force of kinetic friction equals the coefficient of kinetic friction times the normal force. So we have 10.076 newtons equals the coefficient of kinetic friction times 35.28 newtons. And that gives us that the coefficient of kinetic friction between the sliding block and the table is 0.2856. And again, the coefficient of friction is a unitless quantity. And so those were the two things that we were asked for. We were asked to find this coefficient of friction between the block and the table, and we were also asked to calculate the tension in the cord connecting the two blocks. Again, looking at this, there were several pieces to this. One of the pieces was going through and looking at kinematics to get the acceleration, and then it was applying Newton's second law to each of the individual objects to solve for an unknown force. On the hanging block, we knew the weight of the hanging block. We knew what the net force was because we knew the mass and the acceleration, and that allowed us to find the tension in the cord. And then on the sliding block, we now knew the tension in the cord. We knew the acceleration of this sliding block, so we knew the net force on the sliding block, and that allowed us to find the force of friction that needed to be acting on the sliding block. And once we had that force of kinetic friction, we could use the definition of the force of kinetic friction, that it's the coefficient of kinetic friction times the normal force. And we knew the force of kinetic friction, and we knew the normal force, and we were able to figure out what the coefficient of kinetic friction was.